Thank you very much, Gunther, for the introduction. So let me start by saying that Shuwen, who gave the first two lectures, and I realized that for a lot of people in the audience, everything we say is sort of an old hat. On the other hand, for other people, it's very new, but for them, we might be going quite fast. So what the hope is that even though it might be hard to follow, I mean, in case you haven't seen all this, it might be hard to follow at times. It should provide like an overview of the sort of like the basic things you should be looking for. So if you pick up some more detailed treatment, like Marus's notes that Shuwen mentioned, or some other treatment, you know what to look for, what the overall picture is. Okay, so what Shuwen talked about today, so this morning, was culminated in elliptic theory. And so this came in two varieties. One was the scattering picture. So this was this scattering algebra psi ml. And the stereotypical elliptic operator in this, I apologize to Maciek, was Laplacian plus 1, where the Laplacian is a positive Laplacian. So just to make clear for my sign. Anyway, so that was one example. And then, I mean, towards the end of the talk, Shuwen very briefly talked about manifold, compact manifold, or manifolds in general, and compact manifolds in particular. So we had something like psi m. And so this was right in psi 2, 0. And then here an example would be the Laplacian. Would be a nice example, which would just be a second order of psi dio. In both cases, they're elliptic. And in both cases, there's this implies that, I mean, Laplacian plus 1 versus Laplacian, that the operator is Fredholm, in this case between appropriately shifted standard subleft spaces, in this case between appropriately shifted weighted subleft spaces. Okay, so I'm just between appropriate spaces, subleft spaces. And so the goal of my talk is to, I mostly be just in this compact manifold setting, just to have fewer things to write, or ignore non-compactness issues. The goal is to talk about, if you wish, the case of Laplacian minus 1 in the scattering perspective. Okay, so the Laplacian plus 1 was elliptic. The Laplacian, as Shuwen pointed out, was not elliptic, but it's somewhat degenerate. And so it's nicer to take Laplacian minus 1 as the prime well-behaved non-elliptic problem. So to get there, let me start by saying that this Fredholm estimate, so Shuwen wrote this down in terms of parametrics. So this follow from estimates, which look like, say, U in HS is controlled by, so I'm going to call my operator P in psi m. And so this is, again, I'm just going to use the compact manifold version. I mean, you just add extra indices and do all the usual things otherwise. So estimates like this, that U in HS is controlled by PU in HS minus M. So these are elliptic estimates plus U in anything. So I'm going to write H minus N, and you should think that this N is huge. And anything, but in particular, huge is relevant. So it's a very negative, very weak norm. And then the dual estimate, which would be the same. So P elliptic, so this is elliptic. Right? This is if and only if the adjoint, which has symbol just given by the complex conjugate, that this is elliptic. So the estimate here is the same. I'm going to call it S prime. P star now. I'm just going to go with minus n still. So an estimate like this. So it's the same estimate in the sense that this is elliptic, etc. It's actually a different operator. And then the actual Fredholm statement, so Fredholm, so for example, in this case, it would be hs to hs minus m. So this is directly one half of the Fredholm estimate. And the other half would be this. Here you use this with this s prime being the dual exponent of this. So s prime equals minus s minus m. Okay, so this is the the estimative version of the Fredholm theory looks. So when you don't explicitly use a parametrics. So in the non-elliptic operators I'll discuss today, it will be much harder to do parametrices. So this is going to be one purpose of the FIO lectures that we'll start tomorrow. But we do it in a different way, in a more estimative kind of way. Now, one thing I would like to point out before getting there is that, so Schumann introduced various concepts, such as the principal symbol. And so this is the principal symbol. So this was defined as an equivalence class. But it's an important subclass of pseudo-differential operators, so like the Laplacian that Schumann wrote down. So our differential operators in general, I mean, this will be true for all differential operators, is the case when this principal symbol has a homogeneous representative. So we'll assume. And I might even strengthen this various things for the purposes of this presentation. We'll assume that this has a homogeneous. So what does homogeneous mean? So homogeneous degree m. So this is with respect to dilations in the momentum variable. So so let me just say it in the momentum variable xi. Xi representative. And so I'm going to call this little p. And so, once you have two homogeneous degree m functions, which differ by something that's a symbol of order m minus 1, they actually have to do the same. So this is now unique. Just to be slightly careful, so then we have to think of this p as a function really on the cotangent space minus the 0 section, right? So you have to, I mean, apart from polynomials, homogeneous functions have a tendency of not being smooth there. Okay, so so good. One reason I wanted to do this is because I want to talk a bit about the phase in a more detailed phase space picture. So one thing that psi-duos do, apart from giving you elliptic almost inverses, so parametrices, is to localize in phase space. So psi-duos can be used to localize in T star m. So you think of this as phase space. So, I mean, if you want, you can overthink that m is just Rn, and you're doing local analysis if you don't want the manifoldy picture. So how do you do this? So the picture is that, okay, so there's this, so maybe I'm going to use psi 0 for this purpose. So what I might want to do is, given a point, I might want to, in the phase space, I might want to localize near it. But I have to keep in mind that everything is dilation invariant. So I have, my symbols are, to leading order anyway, homogeneous. So I cannot just localize near one point. I really have to take the corresponding ray. So what you really want to do is to think about the sphere or cosphere space, which is just T star m minus 0 divided by dilations. So these are, the dilations are, where you say take x comma xi in local coordinates, comma t, so this is the dilation parameter, and send it to x comma t xi. And so this is positive. Okay, so just dilate in the fiber. And so, so I wrote this as a quotient space. If you don't like quotient spaces, what you can do is to take a representative. So what you really have here, here's my M, and then here's my, this is my Rn. So these are each Rn. So this is the fiber of the cotangent bundle over a point. So I don't know, this is my P. I shouldn't call it P. Z. The fiber over Z. Okay, so this is an Rn here, right? This is, you can identify it using coordinates with Rn. And then, one way to make, and so the dilation orbits look like this, right? You just take a covector and multiply it by scalars. Okay, and then one way to distinguish dilation orbits is to take a transversal to it. So, okay, let's see if I find a. So I want to take a transversal. There's a transversal to it. And what's one way of taking a transversal is I just take a hypersurface, e.g., norm psi equals 1. So the unit cosphere bundle. Now, of course, in a manifold, so this would have to be on a manifold. You just say put the Riemannian metric on and blah, blah, blah. Now, this is totally irrelevant, which shows that it's a bad way, not the right way of doing it. What you really want to think about is what do these orbits do as they go out to infinity? Okay, and then one way to make this concrete, that you're really looking at these dilation orbits and not picking out anything irrelevant, which is somehow morally wrong, is to add, what you really care about is infinity to the picture. So what I want to do is do a compactify the fibers of T star M. So they are Rn, so remember what they call Z. So I have Rn's, and what I want to do is I want to send them into a ball. So this is going to be a ball. And how do you do this? Well, here's my Rn. So these are the dilation orbits. This is the origin. I have all these dilation orbits. And what I want to really do is to distinguish them. So I want to glue a big sphere at infinity. Glue in a sphere at infinity. And how do you concretely do it? So if I call, so remember, this is my psi space. So what I'm going to do is I want to write psi in polar coordinates, except that I want to be near infinity. So I'm going to write it in reciprocal polar coordinates. So I want to think of it as rho inverse times omega. Omega is a sphere, is in the m-1 sphere. And so rho is the reciprocal of the magnitude of psi, so which I can do when psi is non-zero. Okay? And then so I want to use rho and omega as my coordinates, which is valid when rho is positive. But I want to think of, so identify, say, Rn minus the origin with 0 infinity in rho across the sphere. Okay? And then now, rho goes to 0 corresponds to, so corresponds to the statement, corresponds to psi going to infinity, to this statement. And so what I can do is just add in the sphere at rho equals 0. And so that is to say, I want to have a new space, so my Rn bar is just going to be Rn. And then I take the disjoint union with 0 infinity in rho across the sphere, and then quotient out by this equivalence. So this is the equivalence. Identify, so this is Rn, yeah, so the equivalence corresponds to this. So rho omega goes to rho inverse omega. Okay, so the upshot is that I just added a big sphere at rho equals 0, which is really psi equals infinity. But by going from psi to psi inverse, I brought it down to a finite point. So I'm much happier about it. It's not out at infinity where I can just make things wishy-washy. I have to be serious. It's at a finite point. Anyhow, so the upshot is that now I want to think about objects such as principles, symbols, etc., as functions on this cosphere bundle. Or now that I've done this compactification, I have, so this now sits inside, so inclusion, sits inside the fiber compactified version. Sits inside the fiber compactified version, and my cosphere bundle can be identified with the boundary of this, right? So my manifold M has just think of it as the compact manifold, has no boundaries. The only way I get a boundary is by going to the new boundary I introduced by compactifying the fibers. Okay, so we should think of your manifold now, this manifold now. So M is compact. Roughly speaking, it's this compact manifold cross a disk or ball bundle. Okay, and I'm just at the boundary of this ball. Okay, and now the so I mean now things are compact. So you have much less space to do shenanigans in. So what I want to do is, for instance, I might want to think of my principal symbol. So if A is up psi 0, think of its principal symbol, which I'm going to call little a, as a function on this boundary. Okay? Okay, and then now, so I have this, my space now is this, this is the cosphere bundle, but I think of it as infinity in the fibers of the cotangent bundle. And now the way I want to localize, if I say have a point here, this is a point alpha in here. Again, you can always just think that you are working with a finite sphere by choosing a transversal, choosing a Riemannian metric, blah, blah, but it's totally irrelevant. I choose a point alpha here, and I want to localize near it. What I want to do is I want to take an A. So this is 0 out here. This is my function little a. And I want to take my operator A to be a quantization. I think Schuman's notation is Q0 of little a, where little a is supported near alpha. Okay, so that's then you think of A localizes, or really micro-localizes, to a neighborhood of alpha. So you think of it as a phase space cutoff function. Yes? Sorry, yeah, up 0. Very good. So this micro-localizes to a neighborhood of alpha. So really on phase space, on this now fiber compactified. So if you wish, you can always just think of the finite cosphere bundle, but for various purposes for later on, this is actually a much, much better picture. What you want to do is, if you want to localize near a point, you just use a bump function that supports near the point, and then, so like AU is, say, you might as well want, say, it doesn't always matter, say A identically 1 near alpha. And then AU would be then, so the micro-localization of alpha, of U. Of U to neighborhood of alpha. Okay, so now the wavefront set with this, the wavefront set of a distribution can be defined by just saying, so the definition, we say that alpha is not in the wavefront set of a distribution, in wavefront set U, if there exists some operator A, and I don't have to be quite strong that it comes from something identically 1 near alpha. The only thing that matters is that, I'm going to make it order 0 on M. The only thing that matters is that it's elliptic So that just says that the principal symbol of A, so little a, is non-zero at alpha. Invertible, really. If you had, so there's a matrix valued version of a vector bundle valued version of everything, and it would be a matrix and it would be invertible, the analogous word. So if there's a pseudo elliptic at the point such that AU is C infinity. Okay, so by microlocalizing near the point, you get something that's smooth. Now, it's also important to have a finer scale. So here you decide that the good things are C infinity. So sometimes, that's just too much to wish. Of course, sometimes people think it's too little to wish. But anyway, let's do something weaker. So we also say, very similarly, alpha is not in the S wavefront set of U. If there exists an A, again, same thing, elliptic at alpha, such that AU is in the sublab space HS, right? So sublab space is transfer from Rn to the manifold the same way psi-DOs do. Okay, so all right. Now, so this is there exists. So there's one A that's very non-degenerate, I should say. So elliptic has non-degenerate. Non-degenerate at the point, and AU is nice. That in fact implies that all A's that are sufficiently nice, like sufficiently well localized work. So maybe a proposition is that if alpha is not in the wavefront set, say S, doesn't matter, of U, then there exists a neighborhood U, neighborhood of alpha, such that if, okay, so I'm going to say this, write down a notation, then explain it, such that if the operator wavefront set of, I don't know, I'm going to call it B, is a subset of U, then BU is in H. And so B is, such as if B is in psi 0, so I'm just thinking of localizing, so I'm just taking operators order 0, which are localized here, then BU is also in HS. So the picture here is that I have an A, right, that's like this. That's elliptic at alpha, and hence near alpha. And the statement is that there is a neighborhood of alpha, so this is going to be my U. So if I take a B that's 0 outside this alpha, that's going to be this wavefront set. So this B should look like, I don't know, it doesn't have to be elliptic now, something like this, but it's 0 outside. This is my B. Then its corresponding operator, big B, so ob 0 of little b, has the same property. That so certain localized operators keep the regularity. And so how do we define this? So what wavefront set prime? So what Schuben talked about is the leading order symbol, the principal symbol. And so in the Rn context, and then again transfers to manifolds. In the Rn context, so you're looking at Kohn-Nirenberg version. What you would say is that the point, say xc, where xc is, you think of xc as non-zero because you're really going to look at the ray of xc. You're going out to infinity. Okay, so this is not, so it's automatically going to be a dilation invariant. So conic notion is not in the wavefront set of, let me say, ob 0b, if exists an open cone. So conic in the xi. So this is in, the conic behavior is in xi, but the open cone, of course, this total thing is in the total space, in Rn cross Rn, really Rn cross Rn minus 0. Such that this little b is a symbol of order minus infinity, which is to say Schwartz. So let me give a name, cone gamma, in gamma. So the principal symbol captures the leading behavior. So it's being non-trivial, it's saying the operator is elliptic, it's somehow non-degenerate. And here it's saying that the question you ask, is the operator really trivial? If it's really trivial, so it's given by a short symbol, then you say that this point is not in the wavefront set of the operator. Okay, and then it's a simple exercise using the parametrics construction that Shuben described that works even locally in phase space that this property holds. So in particular, if one A works in the definition, then any other A, which is sufficiently well localized, works. Okay, so that there exists, actually, in this case, is equivalent to a for all statement. I mean, there's some subtleties, but that's basically it. All right, so now, very good. So now the, where is that? If alpha is not in the wavefront set of U, then there is a U neighborhood of alpha such that if B is in U, then BU is in HS. Yes, exactly. Very good. So yes. So if you notice anything, I say something and write something else, you comment on that because I tend to do that sometimes. Okay, very good. So now. In x psi, so conic in the second variable. Oh gosh, in gamma containing. Okay. But again, so then, okay, so this is the way you write it down usually, but I think it's just much easier to think about it in this compactified place, because all you are doing, what's the cone? The cone corresponds exactly to a neighborhood on this sphere at infinity, because that's what the real dilation transversal is, okay? That's a real thing. This is the soft thing. All right, so now given this, we want to talk about what happens if, so what if you have a P that's not elliptic. So we want to think a bit like algebraic geometers. So you have something that's not completely nice. So you want to have degrees of niceness. So what's the next step from being not completely nice? Okay, so this, remember, says in this version, this compactified version we have, this is equivalent to the statement that it's, so you take, or maybe I should say just in order in homogeneous language, this is equivalent to the statement that the principal symbol is non-vanishing, right? Because we made the principal symbol homogeneous. Okay, so now i.e. P, which is the principal symbol, vanishes somewhere. Okay, so what you want to say that it's, what is the least degenerate version if you say it vanishes non-degenerately? So the least degenerate version is that P vanishes. So again, remember it's homogeneous the way I'm writing it, non-degenerately. Okay, so i.e. P equals 0 implies that dP. So at a point at which P is 0, dP is non-zero. The differential is non-zero. Now, in terms of the phase space picture, so this psi m is just slightly annoying because there's the m. So when m is not 0, it's slightly annoying. You have to say some more things, which I don't want to say right now. So I'm just going to say the m equals 0 picture. So m equals 0. Then this little p you can think of as a function, as we already done. You can think of as a function on this fiber compactified cotangent space. Okay, and so I have this sphere bundle at infinity. This is my really the boundary of this. Okay, and I'm looking at the 0 set of p. So I'm going to call it sigma. And I'm asking that this be non-degenerately defined. Okay, so dP is non-zero and P is 0. Okay, now, okay, So one thing I didn't say that I meant to say, OK, so vanishes non-degenerately. There's even in the scalar case, there's two things you can do in this meaning of non-degenerate. So what I'll talk about today, we'll talk about when P is real. So there's interesting things you can do when P is not real. The principal symbol is not real, but that has a different flavor. So today I talk only about the real case. And remember that this amounts to that P minus P star. So remember the principal symbol of this is P minus P bar. But if P is real, then this is equal to 0. So this implies that P minus P star is upside one lower order. So this is exactly the case in the operators to leading order self-adjoint, okay, which is the case for a lot of interesting operators in real life. No, not all. OK, so talking about this case, real P, this is the picture. Now, in this case, you can't expect that you have estimates like the elliptic estimates. So instead, new things happen. So the basic phenomenon will be the following. And so this is, again, that uses the notion that Schuwen introduced. So basic phenomenon will be propagation within. Propagation of what? Say of estimates, or singularities, or whatever you want. I'm going to say of estimates because that's what I write down, within sigma. Now, propagation how? Like in what direction? So this uses a notion that Schuwen introduced, which is the Hamilton vector field. So the result will be, so this will be Hermander's theorem, which I state in a little bit. I introduced a new term, so the definition will be by characteristics are integral curves of the Hamilton vector field. So remember, this is the, it shouldn't quite say this way. So let me write it down. This is the Hamilton vector field of P. So this corresponding to the Poisson bracket. So this is defined by HP applied to B, say, is the same as the Poisson bracket of PB. And let me just write down the local coordinate version that Schuwen wrote down. So it's the sum over J of dP dxij dB dxj minus the other way around, dP dxj dP dB. Sorry, I didn't give myself enough space. OK, so and there's a parenthesis closed here. So by characteristics are just integral curves of HP inside the characteristic set, inside sigma. So the thing you're supposed to be thinking is outside sigma, my operator is elliptic. So typically, even if you have a non-elliptic operator, the operator is elliptic almost everywhere, right? So the place where it's not elliptic, certainly in this non-degenerate situation, we have codimension 1, so hardly anywhere. Now, of course, that doesn't mean that you understand everything. So almost everywhere is an extremely weak statement. All the exciting stuff happens on the characteristic set. Okay, so this is the exciting place. And the back characteristics are the integral curves of HP. Now, let me translate this because it's so the way I wrote it, it's easiest to think about this really in just the uncompactified phase space. You're just really taking integral curves of this vector field. But it's much better not to think that way. And so the way you want to think about this is that, first of all, if P is homogeneous of degree 1, so M is equal to 1, a simple computation shows, so I mean in general, so let me just say it. In general, HP is homogeneous of degree m minus 1. So why is that? Well, that's directly because of this formula. So it's the xi j, right? They bring down the order by 1. And here it doesn't bring down by 1, but there's the dv xi j. So that also has the same effect. OK, so it's homogeneous of degree m minus 1 with respect to dilations. And so in particular, m equals 0 tells you that HP is homogeneous degree 0. So what that tells you after an easy computation, simple computation, and then make a comment on this. Yes?
Do you mean minus 1? Or do you mean m?
Yeah, m is 1, yes. So when m minus 1 is 0. A simple computation is that HP is, in this case, HP extends to a smooth vector field up to, so up to means including, right? So up to the boundary of this, which is in fact tangent to it. Okay, so our vector field, which is in principle sitting inside just the cotangent bundle, which has this infinity out there, which you can always think, oh, it's very far away. Let's not worry about it. That would be a disaster. One way of worrying about it without being explicit is to use uniformity, which is how standard estimates go. But sometimes it's just nice to have uniformity automatically, and compactness gives it to you. Right? So algebraic geometers love compactness, topologists love compactness, so we should love compactness too. All right. So. And in general, what you can do is work with. So I'm just going to conflate these things all the time. But in general, you can introduce a new script h or something, p, which is just a rehomogenized version. So let's go ahead, say xi to the minus m plus 1. This removes the homogeneity times hp. Now notice that what happens in terms of integral curves when you multiply by a positive factor, all that happens is they get reparametrized. So in terms of the integral curves, the image of the integral curves, you say, who cares? So this simply same. So same really means up to parametrization. Up to parametrization integral curves. OK, now. So by now, this is really good. So I have this picture, I have this characteristic set. And then within this now, I'm going to have a vector field. So I'm just going to think of this HP, so or maybe capital H in general case. And I have some vector field. Maybe it has some critical points and does things like that. And then the basic phenomenon will be that estimates or wavefront sets propagate or estimates propagate along bicharacteristics. And the slightly more precise version, so it's the Hermann-Der slash Duistermaat-Hermann-Der theorem. Is that, so if P, as we described, so it's non-degenerate in this sense, then you can look at the wavefront set S of u, and then, of course, I mean, you need an equation. If you don't have an equation, you can't say anything. So one way of saying it, let's just assume that PU is equal to 0, or PU is infinity, or whatever. Instead, I'm going to put it this way, minus the wavefront set, sorry, I need an order here, minus the wavefront set S minus m plus 1 of PU is invariant, or is a union, let's put it this way, is a union of maximally extended bicharacteristics. in sigma. So outside sigma, right, we are controlling everything. We have elliptic regularity. So if you know at a point Pu is nice, the elliptic parametric construction, which I said works microlocally, blah, blah, tells you if, let me just say, outside sigma, we have the statement that if alpha is not in the wavefront set of S minus M, it's an M-Solder operator of Pu, then alpha is not in. Then alpha is not in the wavefront set S of U. So if Pu is nice, then U is nice. That's elliptic regularity, microlocal version of elliptic regularity. And for example, it follows directly from the parametrics construction that Schuben described. Okay, so let me just draw a picture. So that picture has too few dimensions. So I'm just going to draw sigma. So the whole board is sigma. I cannot really draw good pictures in general. So my board is sigma, and I have these. So these are my integral curves of HP. And the theorem is telling me, okay, maybe Pu is bad in places. I mean, that can always happen. So life is sometimes not as good as you want it to be. But say this is the wavefront set S minus M plus 1 of Pu. So in other words, Pu is really nice here. Now, then it tells me that if I take a point in there, this is my point. I take a point alpha in here. And if alpha is not in wavefront set S of U, so U is in HS microlocally at this point, then in fact, this whole integral curve segment, so this implies, and then let's try yellow, that this whole thing here is disjoint, let's say intersects VFSU trivially. Okay, so that's the propagation of singularity statement. A different way of saying it, and that's how you actually prove it, a different way, which is the estimative version. So the estimative version will tell you this. So I'm going to redraw the picture just because there's too much on it already. OK, and then here's my point, say alpha. And I know that my distribution U is nice here. And I want to conclude that it's nice somewhere else. And it's going to say I want to conclude that this is my other point beta. And I want to say that U is nice here. So what does it mean? How do I say that something is not in the wavefront set? I'm supposed to come up with an operator that's elliptic at this point. So that's my microlocal cutoff. So I'm supposed to come up with a bump function. So let's say localized here. This is going to be the wavefront set of some operator B1. And I'm trying to say that B1U is nice, right? That's a statement that this is not in the wavefront set. Now, what I need to achieve this is to know, I think that this doesn't show. What I need is to know that I have a region here. So this is going to be a wavefront set of some other localizer B2. And then I need to able to get from the yellow to the I don't know, pink, red, whatever color that is. So I need some other one that looks like this. So this is the wavefront set of B3. So you should think of, I'm saying wavefront set, which of course allows the operator to be 0. But you should really think that everything I'm writing has wavefront set in here and this elliptic in the interior of what I drew. Okay, and then the statement is that you can control B1U is controlled by a constant times B2U plus B3 Pu. And I'm just going to put indices here for the HS. This is the S. This is S minus M plus 1, plus a trivial norm that they have to add. Okay, so n is anything. So you have a control like this, provided that this picture is what it says. So when you start with any point here, take the backward integral curve, and you're supposed to reach a point in the yellow region while staying in the green region. So this is provided that, so let's write this out. This is provided from each point in the wavefront set of B1. So we're non-trivial. We can get to actually elliptic set to a point at which B2 is elliptic by staying in the elliptic set, so where B3 is elliptic. So elliptic set is just where it's elliptic, set of B3. Okay, so if by any point in the red region I can get to the yellow region by staying in the green region, then I have an estimate like this. That's the statement of propagation of singularities. Okay, and the way this arises, well, there's the Hamilton vector field, right? That's the integral curve. Is the way it's proved. So a proof is a positive commutator estimate. So Schuwen showed you that the principal symbol of a commutator is given by a Hamilton vector field. So maybe I spent the last 5 minutes on this just for a very quick sketch, but then I want to now say what happens on a larger scale. So this is all fine, except that I ignored one small possibility. So the small possibility is that the theorem is perfectly fine, but at some point it says nothing. Namely, there are points at which just the fact that the wavefront set is invariant under the flow is the same as that the wavefront set is conic. Namely, which points are these? The points where the Hamilton vector field just points in the direction of the conic dilation, the generator of the conic dilation. So radial points so these are points at which HP is a multiple of the generator of dilations in psi, which is what? So just sum psi j dd psi j. So the vector field has no x component, ddx component. The dd psi component, psi j component is just psi j. It's just going out from the orbits. Okay, from the compactified perspective, or if you want just the transversal picture, but this says that this HP, which remember had some rescaling potentially, is a statement that HP vanishes. Right, so why? Maybe it looks a bit surprising that it actually vanishes when it doesn't look like there. But you have to remember what the compactification does. What the compactification does, we introduce this rho is Xi inverse. And if you do that, and you keep omega were the sort of spherical variables, then if you do that and just work this out, this sum psi j dd psi j just turns into minus rho d rho. Okay, and at rho equals 0, rho d d rho is 0. Okay, there's no ifs, buts, whatever. Rho equals 0 exists. Okay, it's not an ideal thing. It's really there. We compactified our space. So, okay, so now this is one nice thing. So I have this compact manifold now, maybe the boundary of this compactified space. Within that, I have this characteristic set. It's closed. It's a 0 set of something. Okay, so it's also compact. And within this compact set, I have a flow. Okay, so in general, it's a mess. I mean, it's a compact manifold with a flow on it. So in order for things to go well without working too hard, and there's going to be talks later on this week about situations where you have to work too hard, a number of them maybe. So the nicest situation is if this HP flow has a source sink structure. So this means that there are submanifolds L minus, which acts as a sink, a source, let's say, in the dynamical system sense. L plus acts as a sink. So the picture might be like this. Here's my L plus, that's my sink. Here's the L minus, is a source, and the flow is supposed to go like this. If you want to make it into a real picture, think about this as a torus. So really, if I'm in 2 dimensions, my cotangent bundle of fibers will be R2. And then, so the sphere at infinity would be a circle, so it's like a flow in a circle, and identifying its opposite side. So I get this is acting as a sink, this is acting as a source. Okay, so that's the nicest situation, and the reason is because at these sources are sinks. So at this, let's put radial sources sinks. There are versions of these propagation estimates. And what do these versions do? What do these versions do? So they're going to work just like the usual estimate, except, so I wrote down the estimate there. What happens is that there's a threshold quantity. So there's a threshold that I'm not going to write down, except which is equal to m minus 1. So I'm going to call it S0, which is equal to m minus 1 over 2 if p minus p star. So just that the fact that the principal symbol was real said that this is order m minus 1, but let's make it order m minus 2. Maybe it's 0, and then you don't care. But okay, so if it's formally self-adjoint, go down to m minus 2. Anyway, the threshold quantity S0 is such that there are 2 things. If S is bigger than S0, then the estimate holds. So let's give it a name. Star holds. You have to be careful about one point that I'm going to hide. Anyway, star holds even without B2 term. So that's pretty amazing, right? So this theorem, right, it tells us if you know something on where B2 lives, where it's a bump, then you know something about where B1 lives. And this tells you that that near these radial points, you have a version of the estimate. So say near L minus, so you have a neighborhood in L minus. You will have an estimate in which you don't need this B2 term. So you just get an estimate for BU in terms of B1U in terms of PU, which is how elliptic theory worked, except there's a loss of 1 order here. Okay? And if S is less than S0, then star holds. But now what B2 should do with B2, so it's the low regularity. So this is high regularity, this is low regularity. With B2, let me say, with wavefronts at B2, in a punctured neighborhood, of the radial set. So in other words, if you have, so say you have a neighborhood of L plus from which you remove L plus. Say you know there that U is nice, then you can even HS, you can propagate this statement up to, including L plus. Okay, that's the statement. Okay, so the reason why this is nice is because if the reason this is nice is that consequence for such a flow so starting at a region of high regularity, we can propagate them to a punctured neighborhood of the other radial set. So say you start at the source, you get to the sink, or vice versa, and then into this, and then into it, with a small proviso. So provided the inequalities are satisfied. So this S0 for S0. Now, unfortunately, so for example, if I have a P equals P star, my S0 is M minus 1 over 2. And if I have an S that's less than M minus 1 over 2 somewhere and bigger than M minus 1 over 2 somewhere else, I have a trouble if S is a constant. So we might need to have variable or anisotropic Sobolev spaces. May need variable order or anisotropic Sobolev spaces. And so in the talk, I think tomorrow, Semyon Dyatlov will actually discuss this as relates to dynamical systems from a perspective that was introduced by Foer and Sjöstrand, and then further elaborated by many people, including Dyatlov, Zworsky, Guillermo, and others. So, okay. So and then the upshot will be, the upshot is that you get an estimate, end of day. Again, S may need to be variable, but so what? Especially this late into the talk. So you get an estimate like U, HS. So when you piece everything together, like you think of this as a partition of unity, and each piece of phase space you have to get an estimate, and you want to put them together. I'm just going to call it S. Minus n. And similarly for the adjoint, on dual spaces, that's important. On dual spaces, and so the upshot will be Fredholm theory. Okay, so maybe I just have 1 minute or 2 minutes to say something about the how does the Hamilton vector field really enter into this discussion. And so for that, so what's the proof? And I stop with this. So we are computing, let's compute something like PU AU minus AU PU. Okay, so P is my operator, and I'm going to take an A equals A star that's going to be a psi D of some order. And this is the L2 inner product. So I can rewrite this, shifting the A's over. A is A star, so it's just an A if I shift it over. So I get AP. If I do the same thing here, I get a P star A UU. Okay, and then you can expand this as I'm going to write on a commutator, so that would be AP commutator. So it's AP minus PA, but then I have to add it back, so plus P minus P star. So this is where P minus P star enters, like on the radial point stuff. This thing, UU. Okay, and then the principal symbol of this, or maybe I times this, as an operator order m plus m prime minus 1 of I times AP plus the other thing, if I have my signs right, is going to be minus HPA equals minus HPA minus 2 P tilde A, where P tilde is just the principal symbol of this difference over 2I. So this Q adjoint part. Okay, so that's the principal symbol of the commutator, and then what you do is you arrange that this is positive, or has a sign. So maybe negative is definite, has a sign. Because that will let you say that this is a square, something like a b squared, and then you can write this as okay, I should stop here, and then rewrite this as so a square modulo someplace plus e, or maybe minus e. So it's a square where you care, and it's not necessarily a square you don't have a sign where you already have a priori information. Okay, and I think I better stop because the Rafe talk is about to come, but I have the feeling that Semyon Dyatlov will tell you more about the details of this proof. So thank you very much. Yeah, so very good. So that's what I would have done if I had one more minute. So the picture is, so these are my HP integral curves. And then what I'm going to do is I really want to take a function that looks like this along the integral curves, and transversally, it's just a cutoff. Really also you have to add, to get the order right, there's something that there's a weight factor that like norm psi to some power as well. Okay, so here it is. Here HP is negative, decreasing. That's all it means. Here it's positive. So this is where my B2 is. This is where my B1 is. Okay, so that's why basically the estimate is true.
This is